Hi, everyone. This is the Hungry Math Professor here. And today I want to discuss the difference between first order and second order logic. And I just want to remind you that my goal here is not to necessarily teach you first order or second order logic in like the most systematic way. If you find this video interesting, then I am going to encourage you to look at some sources where you can learn first order logic or second order logic very carefully. My goal here is simply to try to help point out that there is a difference and try to just give you an idea of what that difference is. And part of the reason for that is because in mathematics, we do not make a distinction between first order and second order logic, meaning, when we do real analysis or we do abstract algebra, topology, or whatever, we don't make a distinction. Okay, but in mathematical logic or in set theory, they do make a very careful distinction. And again, most mathematicians in my experience are not aware of this distinction. And so I want to make this video because there are some topics that I want to talk about where you may not need a very deep understanding of the difference between first order and second order logic, but you need to at least be aware that there is a difference and why there should be a difference, and maybe some of the consequences of these two things. So that's my goal here, is just to try to give you the idea. And I hope it's useful for mathematicians as well as other people, especially mathematicians, though, who maybe are just not even aware of the fact that there could be two different versions of logic. And by the way, I'm only going to talk about first and second order logic, but there's also things called higher order logic, like third order, fourth order, so on and so forth. Okay, so let me try to start getting into this a little bit. And so in particular, when we do, I'll start with first order logic, but I won't really make the distinction very clear until about the middle of the video. But when we do first order logic, we have to be very careful about what are the symbols we're allowed to use when we make logical sentences and formulas and things. So I have to be very careful about that. So first of all, it will be assumed, so the logical connectives are already assumed to be in our language by default. So what I mean is things like and or and not and implication, and even silly things like parentheses and equals and the for all quantifier and the there exists. And I may even be missing something that you think is important, but my point is just that these typical logical connectives that mathematicians and logicians and philosophers are all familiar with from logic are there. Now, you may choose to only define it in like a very efficient way. Maybe you just choose ands and nots and equals or something, like you may choose to only define explicitly like a subset of these and then define the rest of them in terms of those. Whatever, I'm not going to make a big difference between those kinds of details in this video, but my point is just that the logical connectives will always be in our language when we talk about first order or second order logic. Okay, but then on top of these default connectives, I'm allowed to add a language on top of that. So again, these is the default language, which will always be there. And then I'm allowed to add a language on top of it, which just kind of somewhat vaguely in words will consist of a set of functions, like special functions I want. I'll give an example in a second, special relations that I want, and also special constants. So beyond just the logical connectives, I'm going to allow myself a certain set of functions, relations, and constants in addition to the default logical connectives, and will also allow notably many variables. Now, this countably part is not strictly necessary. I'm just going to restrict it to be countable in this video, but that's not always the case, which these variables take values in some set X. Okay, and so we have a bunch of variables that we're also allowed to use. So we have all the logical connectives, we have whatever set of functions, relations, and constants we want to be in our language, and we always are allowed to use countably many variables in the language and the logical connectives, and these variables will take some value in some set, which that set also needs to be given. Okay, so we're starting to describe what's the kind of thing that you do in model theory, but again, I don't want to be too careful here. I just want to give you the idea. But if you study model theory in particular, I can give you a reference before I get too far along here, which I am following to some degree at times, which is called An Invitation to Model Theory by Jonathan Kirby. Where you'll see the language defined very carefully and the variables issue and what it means to interpret a language in a model, all these things that I want to just kind of give you the idea of without having to go too deep into the detail. So an example, and I'm using the notation of this reference I just gave, I can define the set real numbers, or I'm going to assume that's already an understood set. And then after the semicolon is going to be the language, like so the functions and relations and things that I want to have in my language. So let's say I want plus, and I want so that's a function, right? It takes two real numbers and returns the sum of those two real numbers. Minus, which I'll think of as a function of one variable, it just takes a real number and makes it negative. I want multiplication, which is a function of two variables. And then I want the ability to take a multiplicative inverse. So that's a function of one variable, which returns its multiplicative inverse. I want the special constant 0, the special constant 1, and I'll allow myself the relation less than or equal to. Strictly less than, sorry. So yeah, that's a lot actually in our language. And with that language, now I can try to form sentences out of this. So for instance, how can I express the number 3? Well, the number 3 is 1 plus 1 plus 1, right? Okay, good. And, how can I express the number -3, right? So I just apply negative to 1 plus 1 plus 1, right? How do I find the 1/3, right? I take, 1 plus 1 plus 1, and I take its multiplicative inverse, right? And then if I want to get 4/3, then I would say 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 inverse. Okay, and this gets a little cumbersome, as you can already see, but my point is that if I want to be very careful, very strict, and it's a good thing to do in the very beginning, I'm only allowed to build up sentences by using logical connectives, because those are always there by default, variables, which I haven't done yet, and anything I've given in my language. So in my language, I'm allowed to talk about 0 and 1, right? I'm not allowed to talk about 5 directly without expressing it as 1 plus 1 plus 1 plus 1 plus 1. Okay. So again, though, what I'm trying to point out is that I can get basically all the natural numbers. I can get the integers by just taking negatives of the natural numbers. I can get fractions with a numerator of 1. And then I can also get a fraction with any numerator I want. So I can express basically every rational number in my language, right? There's always this question in logic when you want to be careful in studying mathematical logic. There's always this question of like, what can I express in the language that I've given myself, right? And you won't be able to express everything. There's also a question of like, what sets can I express? And we call those definable sets, right? Because you won't necessarily be able to express everything in your language, right? So for instance, I can express every rational number in this language, as I've kind of already alluded to, but you won't be able to express like transcendental numbers like pi, for instance, right? So um, you won't be able to talk about pi directly, that means. Okay, what else can I do, right? So I can also form stuff like this, right? So x1 plus 1 plus 1 times x2 equals x3, right? I can form that sentence. What else? I can, just to give some more examples, I can also quantify things, right? So I can say for all x1 in the real numbers, there exists an x2 in the real numbers, and then I can say that x1 is less than x2. So what does that say? For every real number, there exists some real number less than it, strictly less than it, right? And that's, of course, a true statement. Now, I just want to say that in first order logic, we often will allow ourselves a shortcut here because this will be true in second order logic too with some caveats. But we're just going to say for all x1, there exists an x2, and then x1 is strictly less than x2. Because I'm only going to allow myself to quantify over a variable which is in the fixed set. So real numbers in this example is fixed. Anytime I quantify, it's assumed that it's in the real numbers. So I'm not allowed to say for all x1 in the rationals, such and such a thing. I'm only allowed to say for all x1 in the reals, and then, um, you know, and that's it, right? So, but that doesn't mean I can't ever quantify over a smaller set. It just means that I have to do things like this, right? So if I want to quantify over, let's say, just the positive real numbers, I would say for all x1, which means it's in a real number, and then I'm just going to require that x1 is bigger than 0. I'm allowed to use 0 here because 0 is a special constant, right? So even though I can't say for all x1 positive, I can basically say that by saying for all x1 in the real numbers where x1 is positive, and then I want to say something about that subset, I can, continue by saying something else, right? So again, we're just trying to be very careful about what we're allowed to do when we quantify. So we're only ever going to be allowed to quantify over the set R in the most direct way, but then we can indirectly quantify over different sets as long as we can express the subset that we want to quantify over in the language in some way. So we can express positive real numbers as I just showed, right? And so to look at a slightly different example that models this kind of thing, we can look at the natural numbers with plus, times, 0, and 1. And again, now I can always express, I only need 0 and 1, and I can express, I only need 1 actually, and I can express every natural number, right? There's 1 plus 1, there's 1 plus 1 plus 1, there's 1 plus 1 plus 1 plus 1, so on and so forth. And notice now I can't express fractions and I can't express negative natural numbers, but I don't want to, right? That's okay. I'm trying to study the natural numbers. And notice I don't need to have a special constant for 4 in my language because I can always define 4 to be 1 plus 1 plus 1 plus 1. That being said, eventually, and in this video, I'm going to want to be I want to use some shorthand for 4 and just use the symbol 4. And that's fine as long as there's a way of defining it in the language. And there is, it's just 1 plus 1 plus 1 plus 1. Okay. Now notice in this language, I don't allow myself the relation less than. Right? In the previous example with the real numbers, I allowed myself the relation less than. Now in this example, I have the set natural numbers. I have a function plus that takes 2 natural numbers and gives me the sum. I have a function times, which takes 2 natural numbers and gives me the product. I have a special constant 0 and a special constant 1. But I can't directly talk about less than. But it turns out that we can define less than anyway, even though I don't have the symbol. So this is just me telling you that I'm about to define what it means for x1 to be strictly less than x3, it means the following. So I want strictly less than, right? So I have to be careful. So first of all, um, sorry, I want x1, let's just say x1 is strictly less than x2, not x3. And let's say, first of all, that all right, let me be very careful. So it is not the case that x1 is equal to x2. I was about to write x1 is not equal to x2. Let me just remind you that technically in the language, I should write it this way. And then from now on, I'll use the shorthand. So first of all, I want to make sure that it's not equal to. And also now there exists an x3. Remember, it's automatically assumed to be in the natural numbers, so I don't have to say in the natural numbers, so that when I add x1 plus x3, I get x2. Notice I need to say that it's not equal because x3 could be 0 in the way I'm expressing the natural numbers here, in which case they would be equal, right? So I just right off the bat disallow them to be equal, but I could also disallow x3 to be 0 in that sum, right? So there's more than one way to do this. But my point is, even though I don't have the less than symbol, I can express what it means to be strictly less than. And so then I can define like a shorthand that anytime I want to say x1 is less than x2, I really mean this sentence that I've just given you, which is expressible in the language, right? Okay, what other kind of things can I do like that? Well, I don't have a divising, the symbol for dividing, right? So I can't write what I just wrote. I'm just writing this as notes. I can't actually write this, but I can express the idea by saying that there exists an x2. Again, that means it's in the natural numbers, so that when I take x2 times 3, I get x1, right? That's what it means for for x1 to be divisible by 3. It means that there's x1 can be written as a multiple of 3, right? And so there you go. That's what it means for x1 to be divisible by 3. Okay. Now, maybe the only caveat I might want to make here now I'm looking at it is that x1 is allowed to be 0, so I should probably be careful and just say, and x1 is not equal to 0. And I'll allow myself to write it that way because that's the same thing as not the case that x1 is equal to 0. Okay, so we don't want x1 to be 0, right? I could also have just put that outside and not allow myself to consider x1, but anyway, this works. Okay, so I want to move now beyond examples, though these two examples I gave, I'd use them for a reason because they're going to be the examples I use to explain the difference between first order and second order logic. Before I do that, though, I have to just say a little bit about relations. And again, if you've never seen relations before, what I'm about to say is not going to do it justice. So this video is really made for people who can at least work with these ideas already. And really what I'm trying to do with this section of the video is to be a little more specific about how I'm going to talk about relations here, right? So given a set, you should think about it as the set that we're fixing in a particular model like I was doing before. So either the natural numbers, the real numbers, or some setting is being fixed. We say a relation. I want to define it in two different ways. I'm not going to prove that they're equivalent, but I'm going to show you why they're equivalent. So a relation there's two ways to think about it. It's just going to be a subset of the Cartesian product of x with itself n times. This relation could be, less than or equal to, for instance, is a relation on x2, or the real number is squared. Or it could be, just one copy of the real numbers, or it could be three copies of real numbers. We can define relations. Or the other way that we can think of a relation is that let's write it like this, where I identify the variables that I'm going to plug in um, explicitly, and the output is either true or false. Now, it turns out that these are equivalent because I can, if I have a relation defined in this second way, right, where I plug in some number which is in x to the n, right? That's what n copies of little x is giving me a something in the Cartesian product of x with itself n times. When I plug it in, if I get true, then that means that that value is in the subset. And if I get false, then that value is not in the subset, right? So these are equivalent ways of looking at things. I'm going to be a little bit sloppy with this equivalence moving forward, especially since in this video I'm not trying to be super careful about every little detail. And so I will interchange these two ways of talking about relations. And just to be clear and make sure that you understand what a relation could be, let's say that x is the real numbers, and then I can think of, let's say R is a subset of the real numbers squared, capturing the less than symbol, right? So then if I write R of 1 comma 2, that would be true, right? And another way of thinking about that is that 1 comma 2 is in the relation. Again, I'm being a little sloppy because I'm using capital R as a function, which returns a Boolean variable, true or false. And I'm also using it as a subset, but I've already explained why that's they are equivalent. So I'm going to continue to be sloppy in this way that I've explained. So I can, of course, R of 3 comma negative 1 is false. And another way of saying that is that 3 comma negative 1 is not in the subset of the real number squared defined by this relation. Okay, and in the case of the natural numbers, I could say that, so that x is the natural numbers now, and let's say that R is capturing evenness. Then, of course, R of 2 is true. Or another way of saying that is that 2 is in the relation defined by R, and R of 7 is false. Another way of saying that is that 7 is not in the relation defined by R. Okay, this will be important in particular when we get to second order logic. So I just wanted to make this clear. Again, if you've never seen relations before, this is probably not enough. But if you just want to try to follow the idea, then it could be enough if all you can keep in your mind is basically the example of less than or evenness and oddness. Like this can give you the idea at least. Okay, so now the question is, what's first order logic, right? So okay, or what's the idea behind first order logic? Well, this is the idea I'll write in words. So when forming sentences or formulas, so again, a sentence usually means there's no free variables. A formula is allowed to have free variables. In a language, you can only quantify over variables in the given set. So I already kind of said this in the examples. This is why I'm allowed to default to not writing where a variable lives, because it's automatically assumed to live in the set that you define, right? So if we go back to this example of the natural numbers, plus, times, 0, and 1, then, let's just go back to an example that we already played around with. we're allowed to say that there exists an x3, for instance, so that x1 plus x2 is equal to x3, right? This is a valid formula that I can write, and it's assumed that x3 lives in the natural numbers, and anytime I quantify in first order logic, I'm not allowed to say anything else. That's why I'm only allowed to say there for all x in the natural numbers, or there exists something in the natural numbers, and I can't do anything else with the quantifiers. Now, again, that doesn't mean that I can't indirectly talk about other subsets. It's just that if I'm going to try to quantify over something else, some other subset, I'm going to have to express that subset in the language somehow, right? So it's not going to be directly in the quantifier like you would in usual mathematics. For instance, you can't directly say for all n in the set of multiples of 3, right? That I'm not allowed to do in first order logic directly, but I might be able to express this indirectly by first saying for all in the natural numbers and then expressing what it means to be divisible by 3, right? So, okay, but the important difference is going to be what I'm allowed to quantify over in logic. Okay, so now let me start to move us in the direction of the difference between these two things. Okay, so now let me give myself a little bit of space and let me just say the following, right? So given any relation of one variable, so let's call that P of n. So again, what's a relation of one variable? You can think about it in this setting as a subset of the natural numbers, right? Or you can think about it as some function which takes a natural number and returns true or false for that particular. These are things are often in logic called predicates. It's part of why P is a good name here. And so what's an example? So for instance, we can take a typical example where P of n is given by the following, right? So 1 plus 2 plus 3 plus dot, 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 all the way up to m equals n times m plus 1. Well, okay, I have to be a little bit careful because I'm not allowed to say divide by 2, right? So let me just, I can write it like this, 2 times on the other side. Okay, I'm being a little stricter than maybe I should at times, but the point is this is an example of a perfectly reasonable relation of one variable, which says that take 2 times the sum of the natural numbers up to n and set that equal to n times m plus 1 and return true if it's true and return false if it's false, right? Notice all this can be expressed very carefully in this language where I would let 2 be 1 plus 1 and 3 be 1 plus 1 plus 1. I have a multiplication. I have all this stuff that I'm allowed to do here. So this is a perfectly reasonable thing that I can express. And then what I want to do with this is to form the following logical sentence, which is going to be P of 0. So I'm saying when I plug in 0 to P, I want that to be true. And for all n, because n is assumed to be in the natural numbers, I don't have to say that. If P of n is true, then that implies that P of n plus 1 is true. And now what I want is that this entire thing implies that for all n in the natural numbers, P of n is true. Okay, this is a perfectly reasonable sentence that I can form in first order logic because every time I quantify here, I quantify over n being in the natural numbers. So this is perfectly reasonable. And now you should identify that this is basically this is capturing the induction principle, except there's one issue, right? So this does capture the induction principle only for one relation P, right? And so, but I want, in order, the induction principle is not about one relation, right? If I fix the relation, and then it's not a principle, it's just induction in one particular case, right? So in first order logic, if we want to express induction and then assume it as an axiom, as a principle in something we want to work with, then I have to do what's called an axiom scheme. So induction in first order logic is given by an um, an axiom scheme, meaning I am going to describe a way of listing out everything I want to be a part of induction. So I don't quantify over P. I simply say that given any relation, this thing needs to be true. And I want each one of those to be a separate axiom because that's the only way I can list them all out, right? So every single instance of a one variable relation P, I'm going to add the corresponding induction sentence, which I just wrote down, right? And that will give me a list or a way of expressing every single thing that I want to be able to apply induction to. Okay. And so that's how you define induction in first order logic. And that has consequences. Okay. So, okay. But then the question is, how do you define this in second order logic, right? So let me switch to talking about second order logic. And again, when we talk about first order and second order logic, it's just really about what can I write down as valid sentences in that logic, right? And so what I'm trying to say is that I'm allowed to write down induction as a set of infinitely many sentences, one sentence for each of the um, predicates that I want to be able to apply induction to. Okay, but in second order logic, I'm going to be able to do this in a much more efficient way. So let me move to second order logic now. Okay, so now the difference is that we're allowed to quantify over what's oftentimes called in the logic community predicates, but this will be basically relations, and that's why I talked about relations here. And so that means induction can be given in the following way. So in second order logic, I can express induction. So let's assume again that I'm in the same sort of language and things. So I'm still talking about the natural numbers, and I have plus, times, 0, and 1. But now I'm using second order logic. So I can say something like for all P of n, I'm not going to be that careful about this, but somehow you have to differentiate between when you're quantifying over a variable versus when you're quantifying over a predicate. It's very common to use capital letters for predicates, lowercase letters for variables. And there's some questions about how to disambiguate all this that I'm not going to get too much into, but I'm going to use capital letters for predicates here, or in this case, this is a relation of one variable, or in other words, a subset of the natural numbers. All these things are equivalent in that sense. So I can say for all, relations of one variables on the natural numbers, P of 0 and for all n, again, this is a lowercase variable, so it's assumed it's in the natural numbers in this setting. P of n implies P of n plus 1. And then I want this entire thing to imply that for all n, again, it's lowercase, so it's in the natural numbers, P of n. And that's the entire sentence, and induction is just that one sentence. So instead of an axiom scheme, which is just a list of a bunch of sentences that must be true to capture induction, I just capture induction with one sentence. Okay, great. So that already gives you a big difference between how you can express things in first order logic versus how you can express things in second order logic. Again, I just want to, in this video, I'm just trying to tell you what the difference is. But of course, there's many consequences to these distinctions, right? And so at the end of the video, I'll just give you a little taste of what some of these consequences are. But then my goal is to um, make videos in the future where I use the distinction between first order and second order logic to express lots of other consequences which are important. Okay, so let me continue now in giving you example of second order logic. So now let me go back to the real numbers and give you the other sort of very typical example, but it's typical for a good reason. So again, I want to be in the real numbers. I have plus, I have negative numbers, I have multiplication, I have the ability to form fractions, I have 0, I have 1, and I have less than, just in case I want to use all these things. And the very important thing that we do in real analysis, your first semester of real analysis, is we axiomatically describe the real numbers in this categorical way, meaning that up to isomorphism, there's only one. And what we need in order to do that is completeness, right? So what's completeness again, just mathematically, before I even try to be careful about the logic considerations that I've been bringing up. So just mathematically, we say, for all subsets of the real numbers, here I'm allowed to just quantify however I like without worrying. S is bounded, so I'm only going to consider bounded sets. Then alpha in R is going to be the sup of S if we need two things, right? If alpha is an upper bound for S, and also if beta is an upper bound for S, then it must be the case that alpha is less than or equal to beta. And I kind of say this in a funny way, but basically completeness means that for any S which is bounded, such an alpha exists, right? So completeness is the fact that there exists such an alpha which plays the role of a supremum for every bounded set S. Okay, so I really just defined what it means to be a supremum here, and then I guess what I can fix this by just saying for all S which is bounded, there exists an alpha that describes completeness. Good. Okay, but this is just, I've just written this in the usual way that we do in mathematics without any worries about first or second order logic or anything like that, right? So now I want to try to take this sentence in just normal everyday mathematical language and try to express it carefully in first order or second order logic. Okay, so let's first try to just define what it means to be an upper bound. So what does it mean to be an upper bound, right? So, and let me just say, before I try to keep it under the rug for too long, we won't be able to define this in first order logic. Okay, so we're going to need second order logic. So first of all, I can define a shorthand which is going to take a set and it's going to take a variable, and it's going to say that for all x2, where x2 is in S, that will imply that x2 is less than or equal to x1. So that's what it means to be an upper bound, right? And I'm being a little sloppy with my parentheses here. Let me even them up. Okay, so what does it mean for x1 to be an upper bound of a set S? Well, it means for any other x2 in the real numbers, if x2 is in S, that implies that it must be less than or equal to the upper bound. Okay, great. Now, what does it mean to be a least upper bound? Well, we already said it in math language, but again, I want to write it in this more careful way So I'm going to do a shorthand, will be LUB of a set and a variable x1. Then that means the following, right? So this is like, I'm going to define what this thing means by saying, well, first of all, it must be an upper bound of the set. And for all x2 in the real numbers, which is an upper bound for the set, that must imply that x1 is less than or equal to x2, right? We just took what we wrote mathematically and just translated it into logic. And so far, everything that we're doing can be written in first order logic, right? Even though, well, okay, I have to be not quite because I'm using the set membership symbol. So I wouldn't be able to do this. I wouldn't be able to use the set membership symbol in first order logic. That's one issue. But besides that, everything else looks fine. Okay, so if I wanted to, I could add the set membership uh, to to my language, but I don't want to do that because anyway, this isn't going to be able to be expressible in first order logic anyway. So then how do I just express completeness? Completeness is given by the following. So I say for all S, a subset of the real numbers, and this is where I can't express that in first order logic. This is the problem. So I can express this in second order logic because S being a subset of R is just a relation. This is just, this is another way of saying for all relations of one variable. Because what is a relation of one variable? It's just a subset of the real numbers in this setting, right? So this is just another way, again, in second order logic, I'm allowed to quantify over predicates. I'm allowed to quantify over relations. And if I'm allowed to quantify over relations of one variable, that's the same thing as quantifying over subsets. So I'm allowed to do that. And then, you know, completeness is just what you think it is. First of all, S better be non-trivial. And there exists an x1 so that it's the upper bound. S comma x1 implies that there exists an x2, which is the least upper bound of this set. And that's completeness right there, right? So for any subset S of R that's non-trivial and has an upper bound, so it's a bounded set, then there must exist a special element x2, which is the least upper bound of that set. Okay, and this is again not expressible in first order logic, but is expressible in second order logic. Even though the empty set, you might think, oh, that's not a symbol I'm allowed, but remember, I'm allowed to define predicates, and I can define the predicate of being empty, so that's something that I can play around with. And so that's perfectly reasonable in second order logic. So this is a typical example when people in logic want to talk about the difference between first order and second order logic. There's two principal examples, which are the ones I've used. You look at induction and show the difference between induction in first order logic and induction in second order logic. Then you look at completeness of the real numbers and point out that you cannot express completeness in first order logic, but you can express completeness in second order logic. Now, there's one caveat to this, which is very important. And my colleague, Brian Wynn, has pointed this out to me, and I appreciate that, which is that the sentence I just said is basically true, but is slightly misleading for the following reason. So completeness of the real numbers in the language that I'm defining here, which is plus, minus, times, multiplicative errors, 0, 1, less than, then I can't define completeness in first order logic. Okay, so that is a true statement. If this is the language that I have with the set of real numbers, then I cannot define completeness in first order logic, but I can define completeness in second order logic like I just did. Now, what's interesting though is that you can define completeness. So here's another example. All right. So what if I want to look at first order set theory? So now I want to look at first order set theory. So my set, a little bit confusing. Now V stands for the set of all sets that I'm allowed to consider. So um, I'm not going to be too precise about what I mean here, but just it's some universe of sets that I'm allowed to consider in my discussion. And I'm allowed to, I have uh, one function, actually, this is a relation which takes a set and another set and tells me whether the first set is an element of the second. And so what's interesting is that completeness of the real numbers can be expressed in first order set theory. Now, I'm going to be very vague about this. I'm not going to try to be too careful, but the one thing I will try to just say a little bit about is notice the language doesn't allow me to say this directly, right? Sorry, that Y looks a little bit funny. Where I'm not allowed to directly say X is a subset of Y. So let's say X and Y are both sets in my universe V. I'm not allowed to form this sentence directly, right? Because I have no symbol less than or equal to. But of course, I am allowed to say for all X, where now little x is some member of the universe V in the language, right? And I can say X is an element of big X implies that X is an element of big Y. Now, I'm using capital letters here in a different way, so it's a little bit misleading. I want to be careful. I'm not using capital letters here to denote predicates. I'm using capital letters to denote sets, and I'm using lowercase letters technically to denote sets as well. But I can, what my whole point is that I can define what it means to be a subset in the language, and so then I can try to quantify over subsets by just quantifying over this particular way of expressing subsets. Okay. And I'm not going to show you exactly how to do this because this is also going to require us to first define what the real numbers are inside of the universe of sets for set theory, and then talk about what it means to be complete in the language. I just want to point out that whenever you talk about whether something's expressible in first order and second order logic, you have to first tell me what's the setting you're considering, right? So if the setting you're considering is the real numbers with these particular this particular language up here, then it's true that completeness is not expressible in first order logic, but it is expressible in second order logic with this language. But if your language is set theory with the element of symbol, then the answer to whether you can express completeness is different, right? And so these questions about what you can express are always relative to the type of logic you're considering and what language you're allowing yourself. Okay, great. Now, to end the video, I just want to say a little bit about, why would you choose first order versus second order logic, right? So far, the way I've expressed things, it seems like second order logic is better, right? I mean, second order logic is certainly more expressive. Like if you just care about what are the things I can express, then yeah, why not just use second order logic, right? So to give you an idea of why that's not the way that we do things, in fact, most people in mathematical logic study first order logic. And the reason is because expressiveness is not the only thing that we care about. We also care about something which we call like the link between the syntax and the semantics. So the expressiveness is sort of like the syntax, like what kind of sentences can I form in my language, right? But the semantics is about like what do the models look like and what does it mean to say that these statements are true or false in these models, right? And it turns out that the relationship between the syntax and the semantics in first order logic is very tight and clean. This is called Gödel's completeness theorem, which is often nowhere near as famous in the broader um, the broader group of people than the Gödel's completeness theorem. But if you're a logician, you know both of these things. And so I'll do a video about Gödel's completeness theorem. But basically, Gödel's completeness theorem says that there is a very nice relationship in first order logic between the proof theory and the model theory involved. And that makes it a very desirable theory. Whereas second order logic, this is known to not be the case. And so things get a little bit hairy. So anyway, at the end of this video, I just wanted to give you some reason to believe that there's a reason why we prefer first order logic over second order logic, because so far in this video, it would make it seem like you should just always use second order logic, right? So there's some good reasons not to do that. I hope this at least whetted your appetite. If you're confused about certain details, maybe you'll dive in deeper, ask me a question on the channel. There's plenty of places on the internet to go to like try to explore this even more carefully. But I'm going to use this now to make several other videos where I'm going to just kind of say first order versus second order logic in passing, assuming you have some idea of what that means from now on, because I've given you at least some idea of what that means in this video. So again, like, comment, and subscribe. Ask me questions if you're not sure about something. Maybe I'll make another video to explain it, or maybe I'll just answer your question in the comments. And I'm happy to engage about these things. And I hope to see you at another video.